Alright guys, this is section 13.1. In this section, our goal here is to be able to use trigonometric functions to find lengths, specifically of right triangles in this section. So the first six, or only six, trigonometric ratios are sine, cosine, tangent, cosecant, secant, and cotangent. Okay, so the first three on this side, an easy way to remember is through SOHCAHTOA, okay? And through SO, that means S for sine, O for opposite, and H for hypotenuse is our SO. CA is the C in cosine, the A in adjacent, and the H in hypotenuse. And TOA is the T in tangent, the O in opposite, and the A in adjacent. So these six trigonometric ratios are just ratios of the side lengths of a right triangle, depending upon the angle that we're given, and that angle is what we call this little symbol here called theta. Okay, so we call this theta, and it's representing an angle in that right triangle, and we're using that to reference the opposite side versus the adjacent side, and of course the hypotenuse in the right triangle. So the other three on this side, though, cosecant, secant, and cotangent, those are normally the three that we learn in Algebra 2 compared to geometry. Okay, cosecant is the flip-flop of sine. Okay, we're going to flip over the hypotenuse over the opposite side ratio. Then the secant is the flip-flop of cosine. Okay, and how I kind of like to remember which one goes with which, or which is the flip-flop of what. Cosecant starts with C and sine starts with S. Those are the flip-flop. Then if you look at secant, it starts with S and cosine starts with C. So that's its flip-flop in letter. Okay, so that can kind of help you remember which goes with what. And then cotangent is the flip-flop of regular old tangent. And that's kind of easier to remember because tangent is in the cotangent name. So again, these three new ones, cosecant, secant, and cotangent, they're just the flip over of sine, cosine, and tangent, respectively. So for example, when we got this right triangle here, and we're going to first evaluate all six trigonometric functions referencing our angle theta in our triangle. So first we need sine of theta, or cosine of theta, and tangent of theta. And then we're going to use our cosecant of theta, our secant of theta, and our cotangent of theta. And it always kind of helps to keep them all together with their respective trig function. Okay, so if I look at the sine with respect to my angle theta here, I have that my side opposite has side length 12. My adjacent side helps make that angle. Okay, so this is my adjacent side. And then of course we have the hypotenuse. Okay, but I got 2 out of the 3 side lengths, and I'm working with a right triangle. So what I could do is use the help of the Pythagorean theorem. So a squared plus b squared is c squared. So if you assign one of the legs to be a and the other leg to be 12 or b, we're trying to figure out hypotenuse c. So 5 squared is 25, and we're adding 144, or 12 squared, and it's supposed to be equal to the hypotenuse squared. Okay, so 25 and 144 is 169. And in order to figure out c, or the hypotenuse, you could take the square root on both sides. And 169 is a perfect square, so the hypotenuse side is 13. So now we can do the 6 trig ratios, okay, because now we have all 3 sides. So sine, I need SO, okay, or opposite over hypotenuse. So the opposite side was 12 over 13. Cosine, remember, was CA. So adjacent side, which was 5 over hypotenuse 13. and tangent was TOA. Okay, so opposite, which was 12 over adjacent side 5. Okay, then if we do the cosecant, we're doing the flip-flops. Okay, so if we do the flip-flop of sine, that's our cosecant. So hypotenuse 13 over opposite side 12. Secant was the flip-flop of cosine, so hypotenuse on top over adjacent side 5. And then cotangent was the flip-flop of tangent, or the reciprocal, so 5 over 12, which was the opposite side. So here we have all 6 of these trig ratios for our given triangle here. Okay. In example 2, if theta is an acute angle of a right triangle and the sine of theta is 4 over 7, what is the tangent of theta? Okay, well, let's draw that triangle out. We don't even have anything to picture it with, so go ahead and draw it out. We know it's a right triangle because we're dealing with all 6 trig functions, and it tells us that the sine of theta is 4 over 7, so let's make one angle theta. That's not the right angle, okay? And they say the sine, or if you remember, that is so, which is the opposite on top. So opposite angle theta is 4. That's the opposite side. And then hypotenuse is on the bottom, so our hypotenuse is the longest side across from the 90-degree angle. So there's our hypotenuse, 7. Okay, and they want to know the tangent of theta. That's TOA, though. We have the opposite, but not the adjacent side, which helps make that angle theta. Okay, so what we're going to have to do is figure out, well, what is that adjacent side? Okay, so if we go ahead and do that, we can do or assign the shorter leg to be A and our other leg to be 4. In the Pythagorean theorem, it's supposed to equal 7 squared, or hypotenuse squared. So 4 squared is 16 and 7 squared is 49. And if we subtract that 16 from 49, we're going to get 33. But if we take the root of that, I'm just going to leave it alone because it's not a perfect square. So I have that A is the root of 33. Okay, but if they want tangent, the tangent of theta, I'm going to have my opposite, which is 4, out of my adjacent, which is the root of 33. But this is where we cannot have any roots in the denominator. We learned that back in chapter 4. So we're going to have to rationalize it by multiplying by that same root in the numerator and denominator. Okay, so we're going to have 4 root 33, and then that root 33 basically squared. But a root and the square go away. Okay, so we're left with 4 root 33 all over just regular old 33, and we got that root out of the bottom. So here is our tangent of theta, 4 root 33 all over 33. So if you have a root in the denominator like that, make sure to rationalize it or multiply it by itself in the top and bottom in order to get that out of there, because we can't have roots in our denominator. All right, we do have a couple of special right triangles. We have what we call the 45, 45, 90 degree right triangle. Okay, so that's the first one here. Basically, the two legs are the same length, but if you find the hypotenuse, you just take that length of one of the legs and multiply it by the square root of 2. Then our other one is a 30, 60, 90 degree triangle. Okay, where the shortest leg is just a multiple of 2 of the hypotenuse, but if we take that short leg and multiply it by the root of 3, that's our longer leg. These are special triangles that you'll see everywhere with trigonometry, so it's pretty good to know them. And here are their special values of special angles that we have. So for instance, if we want the sine of 30 degrees, okay, well that's 1/2. Or if we want the cosine of 60 degrees, well that's still 1/2, okay. The tangent of 45 degrees is 1, and on and on and on. So these are the 6 trig functions that allow us to get 30, 45, and 60 degree angles very quickly. These are the most known ones, so it's very good to keep this on hand. So in example 3, it says to solve triangle ABC. When it says solve like that, we're going to find all the angles and all the sides. Okay, so in this triangle ABC, we got angle A and we got side B. Okay, so let's try to figure out what the heck angle B is. Okay, well, we know that 180 degrees makes up for the whole sum of angles in the triangle. And we know 90 of it, and we know 28 of it. Okay, so I know that the other two angles have to sum to 90 because we already have 90 right now. Okay, so basically, the other two angles account for 90, so I'm going to subtract the one I know already, which was 28. Okay, and we get 62 degrees, which is angle B, or big B. So now we know all the angles. That was 62 degrees for angle B. Okay, now we're going to go on a hunt to make side length A and side length C. And from there, you could pick whatever acute angle you want, 28 degrees or angle B, which is 62 degrees. So let's just say we pick the tangent of 28 degrees. Okay, because our side opposite of that is A, and we don't know that yet. And our adjacent, because we need opposite of our adjacent, which is TOA, our adjacent is 15. Okay, so in order to get rid of that 15 real quick to solve for side length A, what we're going to do is multiply 15 times the tangent of 28 degrees, and it's going to equal A. Okay, so this is where the calculator is going to come very in handy. So if you go to your calculator, make sure to go to mode and then all the way down to degree and hit enter. We want it in degrees because that's what we're dealing with. Then hit second quit. So now what we want to do is do 15 tangent, and here's a tan button, of 28 degrees. And if we hit enter, and let's say we round it to the 100th, okay, that is 7.98. That was our side length A. So here's side length A, 7.98. Okay, and since we were given angle A, let's use the cosine, or ca. So adjacent over hypotenuse of 28 degrees. So the cosine of 28, we need adjacent on top, which is 15. And our hypotenuse, we still got to figure out, which is C. Okay, so in order to figure this one out, I can multiply by C on both sides. So I got C times cosine 28 equals 15, but I can divide both sides by cosine 28 degrees. Okay, so C is going to be 15 over the cosine of 28 degrees. Okay, so we need that in the calculator now. So alpha y equals 15 over cosine 28, and we get 16.99, which is about 17. So it's about 17. And we don't know what units, so this is just 17 is equal to C. Okay. So now we know that angle A was 28 degrees and its corresponding side length, little a, was 7.98. Angle B was 62 degrees and little b, or its corresponding side length, was 15. Angle C was our 90-degree angle and its corresponding side length, little c, was 17. So here's all of our completed triangles. So we solved the whole thing, all angles and all sides. All right. So in our word problem here, while standing at Yavapai Point near the Grand Canyon, you measure an angle of 90 degrees between Powell Point and the Woodforce Point, as shown. You then walk to Powell Point and measure an angle of 76 degrees between Yavapai Point and Woodforce Point. The distance between Yavapai Point and Powell Point is about 2 miles. How wide is the Grand Canyon between Yavapai Point and Woodforce Point? Okay, so they outlined the triangle for you, and we're trying to figure out x on this side. So we know an angle, and if we look, x is the side opposite of that angle, 76 degrees, and we do have the adjacent. So what angle uses the opposite side and adjacent side? Well, that's the tangent. So we're going to use the tangent of 76 degrees, and it's going to be opposite, or x, over our adjacent, which is 2. And we talked about earlier, well, to get rid of that 2 really quick is to multiply it on both sides. So 2 times the tangent of 76 degrees. Okay, so we're going to have to do that in the calculator now. Tangent, or 2 times tangent of 76 degrees. And if we round that off, that's about 8. So it's about 8. And we can't leave it naked. We were working in units of miles. So this is 8 miles. That's how long or how wide the Grand Canyon is between Yavapai Point and the Woodforce Point. In our last example here, example 5, we have that a pair of sailors attached to a boat with a rope 300 feet long. The angle of elevation from the boat to the parasailer is 48 degrees. Estimate the parasailer's height about the boat. Well, first thing off the bat, we don't have any sort of picture. So go ahead and draw one out, okay? We need a right triangle because that's what we're dealing with right now. And the parasailer's up in the air. So if you kind of sketch him, he's up there, okay? Then we have the boat in the water, okay? And it says the rope that is attached to the boat and the parasailer, that's this side over here, that is 300 feet long. And then it says the angle of elevation from the boat to the parasailer is 48 degrees. And why I'm putting it here is because it's going up. That's what it means to elevate, okay? Look up. So we're looking up at the parasailer. And then it wants to know, well, estimate the parasailer's height about the boat. So we don't know this side or height there, okay? So if we compare it to our reference angle of 48 degrees, that's our theta. Well, this is the side opposite. And we have the hypotenuse, which is the longest side across from the 90-degree angle. So what trig ratio uses opposite and hypotenuse? Well, that is our or our sine. So sine of our angle, which is 48 degrees, is equal to our opposite, which we don't know yet, over 300. And again, to get that out of there, multiply by that 300 on both sides. So we got 300 times sine of 48, and it's got to equal x. So one more time in the calculator, we got 300 times sine of 48 degrees, and if we round it up to the nearest foot, let's say, okay, that is 223 feet. So 223 feet, and that's about, so 223 feet is how high he is from that boat to wherever he's at up top there.